Okay, good morning, good afternoon, students. Um, do you have the Im- the lecture slide? Okay. Still fussing around with this display up here. Things are working better now, though. Get your clickers ready and your calculators. We're going to do some calculating in just a few minutes. You'll notice that the quotation of the day from Albert Einstein is he was kind of a wiseacre. The difference between stupidity and genius is that genius has its limitations. I think he was talking about politicians. I can't be sure, but probably he was thinking about that. Anyway, he's going to be the quotation of the month person for the month of October, if you haven't already figured that out. Okay, a few things for the good of the order, housekeeping wise. Shh, 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 shh. There is a lot of clicker data that I have not uploaded yet, basically between lecture 8 and lecture 13, plus today's, we're going to be clicking today. So I've got a lot of it worked out, and I just haven't uploaded it and stuff. And the reason I'm a little bit behind is I usually do it on Wednesdays during office hours, except that the last 3 weeks we've had plenty of people coming into office hours, so I'm always working on something with students instead of office work. But we'll get it done. And in case you're wondering, no, you don't have zeros. It's just that they're not uploaded yet. Another thing I want to go over with you are the blurb sheets. And in this particular section, section 2, they're not ready yet because of the fact that we had to regrade everything. So I'm not sure how I'm going to make blurb sheets for you guys, and I think I'll do that this afternoon after lecture. By the way, if you feel like coming over to talk to me about anything after lecture today, you can sure do it. I have your printout. You student athletes, I have your printouts, your spec sheets for your grades and stuff. So get it right after lecture. I'll just put this over here. So the blurb sheets, they look like this. This is what they look like over here. You'll see them. It's a PDF, and it's basically the answer key that my test writing software generates. So when I print out the test for you guys and then get ready to photocopy it, it prints out the test that you see, and then it prints out this. And that's what then I go and take this part, the key, and fill in the Scantron and give it to the test scoring guys, and that's their key. So here's a close-up of it. The matching doesn't have a blurb, but the true false and the multiple choice do. And as I've mentioned before, it gives you the gist of each question, but not the verbatim text of the question itself. All right, and that actually is not, even if I were to give you, or publish the tests, I would still only do this. This is the study tool that I want you to try to have in reserve for final exam week. Because if I gave you verbatim questions, you'd want to memorize questions. And then if I make a similar question but not that same verbatim text, you're SOL. But this way, if you think of the concept for each question that you may have gotten wrong and then do a little extra studying on that concept, you'll be a lot lighter on your feet than if you just memorize. Remember, think, read carefully, think carefully, and you shall prosper on exams to the fullest extent that you can. So true, false, and multiple choice have blurbs. And you'll see them probably tonight. The section 1's already up because I didn't have to regrade them, but you guys had to regrade. It looks like this. Here's the page. So you guys are going to be over here in the section 2 column, and I'll have a similar list for you guys, and we'll do the same for exam 2 and exam 3. Not the final though, of course, because we won't be giving out exam printouts for the final, and we won't have a class meeting after the final. So, but exam 1, 2, and 3, yes. Questions about any of that? What was that? Was there I saw a bug flying. Oh gosh. I'm sorry. That row, you guys are frightened of bugs. I saw not you guys are the spider girls, but sitting next to she looks, oh, it's right on top of me. Sorry, I saw something come down from the ceiling. Do you know that there was in one of the other lecture halls, I can't remember where it was. There was this huge bug in there in the room. And I think it was classroom building one of the big lecture halls over there. And man, did it almost caused a stampede. Yeah, question. The question is, we don't learn about bugs and organisms and stuff like that in this class. Why are there two different kinds of physical science? There shouldn't be. You know, very few, in the old days, if you were, like back in the day of Thomas More, 1500s, Thomas More, the guy that lost his head in England because he wouldn't go along with King Henry VIII, he was actually the tutor of King Henry VIII in math and astronomy, and he was a lawyer, he was a legal scholar, and the head magistrate of England, but he was also up on all this. And in those days, then a doctor of philosophy would be equally adept at lecturing about bugs as about lecturing about F equals MA. But in this day, things of this information is so intense, is so voluminous that, in other words, it's ginormous, big, that you can't be a master of all the disciplines the way you used to be able to. So you can be well versed in all the disciplines, but you can't be. We should have a generalist PhD, but now they're organized by discipline: physics, chemistry, biology, and so forth. So that's why. But in the olden days, yep. Lecture one day on bugs, and the next day F equals MA. All right, I got some bad news for you. Not just bad news, but a big disaster, and that is that Miss Darian, our faithful and trusty and excellent, awesome TA, will not be having office hours until further notice. And in fact, she won't be TAing at all due to some bureaucratic stuff that it's basically my fault. So if you liked Darian and you can complain to my boss about me not making the paperwork right. So I'm going to try to get them to change their mind in the physics department, and maybe in the next week or two we'll get things sorted out. But for right now, for further notice, no Darian. So try not to cry a river of tears. She is a great TA, very helpful to me, very smart. All right, let's keep going to the stuff we were talking about last time. We talked about conservation of momentum as a special case brought out by the impulse equation. F net times delta t equals delta p. So if there's no net force, delta p is 0. And if that's the case, you can model that with a lot of physical systems, or use that to model a lot of physical systems. And the example that we worked on was this one, the train cars. The momentum state beforehand would have to be equal to the momentum state afterwards. And in between, before and after, is the interaction where they latch together. And if you've ever been down to the freight yard, you know when those things latch together, it's a big bang. It's a really loud noise, a lot of energy for that. But theoretically, that kind of interaction force, a little bit to the left for boxcar 1, a little bit to the right for this string of 3 boxcars already hooked together but at rest, those newtons will cause accelerations left and right and changes in the velocity states left and right. And the most efficient way of studying it is by looking at the momentum. So let's do that. Here's the initial momentum state, P subscript I. Plus sign denotes rightward, and most of our most of our examples and questions on homework, questions on exams will be one-dimensional. So pluses and minuses will be all you have to worry about. Guys, engineering majors taking physics 2048 or pre-med majors taking 2053, they would have to worry about trig, 2 or 3 dimensions. But for us guys, 1 dimension is going to be good. And so, all right, you've got this interaction force, and supposedly that means that delta P is equal to 0 because, as we noticed last time, as we made note of, the gravitational downward newtons are balanced by the upward rigidity newtons from the train track. All right, so in that case, the final momentum should be the same as the initial momentum. And what we did was figure out from that the final velocity, or the new velocity, V subscript new, for the set of 4 boxcars all latched together. And I believe for this one, if you look back in your notes, this one was 1.1 meters per second for V new. Now I want to go forward and take a look at a tackling problem. And you had some homework with tackling. Examples, running backs and stuff like that. I think it was 5, problem 5. I can't remember exactly which one. You were to, or 6, you were to calculate the total momentum of 2 football players, but heading toward each other, so opposite directions. The train track example was one thing moving to the right and the other thing at rest. Football, it's 2 guys heading for each other, trying to tackle. Now, what we're going to do in this next example, I'm going to model a running back and a defensive back, a DB, with a pair of, basically I'm going to use a dot to represent the center of mass of each guy. And believe it or not, the center of mass of most human beings is your belly, right about your belly button, or at the level of your belly button. So it's not chest high, it's not knee high, it's belly button, right about where your belly button is. And because that's where your umbilical cord attaches, center of mass. Anyway, so that's what we're going to do. Here it is. Here's our setup. Here's my table of initial information, my initial conditions. The running back, I just said, well, let's think of a running back running pretty fast, 8.3 meters per second. That's getting along. An Olympic sprinter is going to run about 10 meters per second. So Usain Bolt is going to run maybe 11 meters per second. So a college running back, 8.3 meters per second in short bursts. Yeah, that's not too bad. The DB is running to the left, and he's not as fast. Negative means left, and in this particular example, and he's only going at 7.8 meters per second. So the masses are 77 for the running back and 86 kilograms for the dB. So the dB is a little bit bigger, a little bit slower, but they tackle and collide. Here's a diagram over here on the upper right. Initial conditions, big letter I in the middle to represent initial conditions. And these two arrows, they look the same maybe to you, but I actually measured them out. One of them is 83 pixels and one of them is 78 pixels and points leftward. So those are true proportions. And then here's the dot representing the center of mass for the running back, and this dot on the right represents the center of mass of the defensive back. All right, so what they do is they tackle, and the DB holds on to the running back and hopefully doesn't get shaken off by the running back. So we'll assume that those guys basically form one big dot after the interaction. All right? And so for that reason, this fourth column, which is the defensive back running back combo, the mass of that after the directly after the tackling interaction is 163, basically the mass of each guy added together. Okay. Now, just like the box cars in the example from class, they all four of them hooked together and you had a total mass of 140,000 kilograms. Here, these two guys tackle and hold on, and total mass 173 kilograms. All right. Now, the question that we want to figure out is who wins? Does the running back win? If so, the final momentum will be rightward. Does the defensive back win? If so, the momentum will be leftward. In other words, a negative number. So let's see what we can see here. Now, the tail of the winner, as I alluded to, is told by the momenta. So we look at the momentum for each guy, add them together, using pluses and minuses carefully to denote directions, and then see what the numbers tell us. All right? If the numbers come out positive, the running back wins. If they come out negatory, the DB wins. So here we go. Momentum number one, up here in this fourth box down in the second column, the initial momentum of the running back, basically his mass times his speed, and it's positive. And I'm leaving the positive signs out in here to save a little space, but you can put it in if you like. Positive 639.1, and the units are kilogram meters per second. For the DB, he gets a negative number, negative 670.8 kilogram meters per second. Negative again, meaning that he's going leftward. And so what we want to do now is add them together. Question over here in the middle. Do you have, good. Ask a question. Always ask a question if you feel like it. You know, it's good. I saw you coaching your neighbor there. That's great. I love seeing that too. I love questions. I love seeing what you guys were just doing. All right, so let's add these two numbers together. Now, do you have your calculator out? Don't let me catch you napping. And I want you to be alert so that you can catch me napping if I throw a blooper, which happens. You guys have seen it. So don't let me catch you nap. So verify this stuff as we go. And, okay, anybody verify me? Negative 31.7 kilogram meters per second. All right, so now we know who wins, because after the interaction, that should be the same momentum. So this total momentum of the DR-RB combo initially is negative 31.7. Just add them together. Or as somebody said in discussions, subtract the chicken. Did you see that? The things I see in web courses. Anyways, so subtract the dB's number, 670.8. Now, theoretically, that is, by conservation of momentum, the same as the final momentum. So this bottom right-hand corner should be ditto marks with the other red cell. Okay, so they should both be negative 31.7 kilogram meters per second. All right? And that's under the theory that you're neglecting, friction from the grass and, other stuff. But, for just a second, yeah, this should hold true. Now, if you want to figure out the final velocity, yeah, okay, not a problem. Just use the definition of momentum, P equals mv. For this new momentum, P down here, negative 31.7. But don't use the same mass as you had before. You have to use a new mass. I colored it blue. I don't know if you guys can see the blueness. But yeah, you have to use this mass, 163. So 31.7 negative divided by 163 kilograms is negative 0.19 meters per second. So if you want to figure out the velocity, yeah, you can do that too. All right. So we know who wins. It was the dB in this particular example. I want to give you another example on the clicker, and I want you to calculate this and make a decision with another slightly different tackling interaction. But before I do that, I want to pause for questions. I see a lot of you guys with your neighbor pointing at something and just double checking something. Raise your hand if you have a question. Colin. The question was, what did I divide 163 by to get the negative 0.19? The answer is nothing. I didn't divide 163 by anything. I used that as the divisor of 31.7 negative. So negative 31.7 kilogram meters per second divided by 163 kilograms is this. Okay? Another question. Okay, let's keep going. We'll get your clicker out. And we're on frequency BB. Christian Chang, are you here? Yeah, you're on now. So yeah, I checked it, and you were on Tuesday. So good. Finally. So get your clicker out, get your calculator out, and just jot this stuff down in your notes. It'll be a good study example with a neighbor if you have a study group. Frequency BB. Hold the power button down and get the flashing square, and then type in BB, and you'll be on the Nitro network. Okay, here we go. Calculation. Enter a numeric answer. Pretty sweet looking tackle there. I think that's Ray Lewis tackling somebody up in Denver. I don't know. Somebody before Demarius Thomas. So this is maybe 10 years ago or something. I can't remember that guy. Really tall and skinny, but a really good wide receiver. But in this case, he got depleted. So wide receiver number 88, mass is 88 kilograms, runs at 19 meters per second rightward. And linebacker number 58, mass 100 kilograms, runs leftward at 16.5 in order to tackle number 88. So who wins? All right, calculate the total momentum and type in the numeric part of that to the nearest tenth. And use the minus sign to denote leftward. And Let's see how you do. And if I were you, I'd jot this stuff down in your notebook. So sharing answers is nice in class, but if you do that on a test, it's not so nice. And the person that you're sharing with in class, when it comes to the test, I'm looking at you. When you do that on a test, they're not going to be able to do it on a test. They're going to be SOL. Don't look back there. I'm looking at you. So, it's nice to collaborate and stuff, but don't just give answers away for free. Just so you can type, because you don't get any more points because you type in the correct answer. You get points from participating. All right. But on the exam, you got to be able to do it. So, giving away an answer without explanation is not really helpful to anybody. I see somebody in the back row just got their mouth all. Yeah, that looks better now. Now she's smiling. Good. All right, that looks better. It looked like you were in thought. Okay, good. I got you right where I want you. If you're thinking, that's exactly what I want. 30 seconds. No, 45. I'll give you 45 seconds. Valeria. Are you the captain of the team back there? Who's the captain? Akeem, who's the captain over there? Who's the brains of the operation? All right. All right. 20 seconds. What's that? One more minute? You want another minute? Okay, I'll give you another minute. Hurry up, move it. Having a transcript is nice, except that all my really weird jokes, screwball remarks go onto the transcript as well. You did? Sarah, you ready? Not yet? Back row. You guys in the back row. You ready? Ready? You guys over here in the front row. You got it in? Has she got it in yet? Did you get it in yet? You got it? You sure? All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh my good. Uh-oh. Well, you guys are geniuses. The answer is 22. So a guy up here in the front, oh yeah, 22 is what I got. And I said, are you sure about that? And did I shake you? He changed his answer. That's the reason I do that. If you don't, if you're not confident of your answer, I do that for a serious reason. if you're not confident of your answer, do you really know it? You know? So don't let me shake you. Now, my comment to you is that you guys are geniuses. The morning class got 73%, so you guys got 74%. Nice. Plus, there's a couple people down there with negative 22. Two people. You got your minus signs mixed up or something. I don't know what you did. Anyways, answer to that is number 22. Here's how it works out. P equals mv. For the wide receiver, mass is 88, speed is 19, it's positive to the right, total 1672 kilogram meter per second. And then, okay, the linebacker is mv, but for him, his velocity is negative 16.5. Ooh, I wonder if anybody just added them together without a minus sign. That would be 3,322. If you answer 3322, you messed up your minus signs. Anyways, this is 1650 negative kilogram meters per second, and so just the sum of those two, P subscript I, and that's the same as P subscript F. And so the question is, who wins? Number 88, unlike in that picture. Now, final comment before we change to a new topic, energy, is this. You will have more problems like this on homework. You'll have homework for the weekend available by lunchtime tomorrow or so. You'll have exam questions on exam 2, probably involving some kind of a momentum calculation. Could be tackling, could be boxcars. You know, it could be something, it could be a chicken floating through space like the homework. So, but be alert. It's definitely something you want to know and remember. Another thing that you want to know and remember is energy. Now, I'm going to just ask you to look at that picture. What do you see in that picture? Don't look at me. Look at the picture. Come on. Yeah. What do you see in the picture? What do you see? Dante, what is that? In the corner? You mean up here? Right here? You can't see that? Oh, man. Okay, sorry. It's yeah, it looks like Tour de it is. It's Tour de France or maybe some other big road race over in Europe going up in the Alps or maybe the Pyrenees. And if you look carefully at it, and I'm sorry that this image with the lights in here, it's just hard to see sometimes. They're going uphill, and the reason that you can see that is these cars down here on the left are about the same distance from the camera as these bikes up here, and this is just a big mass of guys. Can you imagine what would happen if, like this guy right here in the front, if he blew a tire and then tumbled, and it would just total, talk about your chain reaction accident. That would shut down the race for an hour or so. But these guys are going uphill. And for those of you that are born and raised in Florida, a hill is this thing where the ground goes up towards the sky, and we have something called elevation. And these guys are going uphill. So let's talk about going uphill. All right, so let's all go to Claremont on bikes. And if you go to Claremont, you can go up some good hills out there, actually. And if you do that, at the end of the day, your muscles are going to be kind of tired. Because to go uphill, you have to exert muscle power. But what's the thing that you've got to have if you want to exert muscle power? Well, you got to eat some food. You got to do some carbo loading or drink some Gatorade or eat some beef jerky, pizza, you know, Chick-fil-A nuggets, whatever, you've got to have some kind of food. But food isn't just food doesn't just appear out of nowhere. It comes from animals and plants. Chick-fil-A, chicken. It comes from chickens. And what do chickens eat? They eat, I don't know, what do they eat? Chicken feed. That's like vegetables or something. So yeah, you need muscles, but if there's not some plants or animals in the food that you eat, somewhere down the line, you're not going to have any energy. And where do they get their energy from? Well, it all comes from photosynthesis. The chickens are animals. They don't do photosynthesis, but they eat plants, and plants do photosynthesis. Salmon in the ocean, anchovies, they eat plankton, and plankton operate from sunlight, I believe. Some of them do, phytoplankton. So photosynthesis. And photosynthesis, but you're still not at the end of the story. You're not at the center of things. Because photosynthesis doesn't happen in a dark room. It only happens where there's sunlight. So photons of sunlight are required for photosynthesis. It activates the chlorophyll molecule and starts a chain reaction that produces some hydrocarbons, some carbohydrates. Carbo. All right, and that's what chickens like to eat. Here's a question for you about chickens while you're jotting down these notes. Why did the chicken cross the road? To get to the other side, everybody knows that. Why did the T-Rex cross the road? No, it was the chicken's day off, so. That's one of my, I only know like about 4 corny jokes. That's one of them. So, photons from sunlight, they're just not out there floating around in space. Like this blob of, this ocean of photons, washes ashore on the planet Earth. And no, it comes from the sun, most of it, a little bit from starlight, I guess, but most of it from the sun. And the sun has photons streaming off of its surface because of the nuclear fusion reactions in the center, in the core of the sun. And that is where the energy comes from the sun, through space, 93 million miles, to Earth, into the plants, into the animals, into your beef jerky, into your spaghetti, your lasagna. Ooh, lasagna. I haven't had lunch yet. I've distracted myself. Into your food and then into your muscles. So, yeah, it's possible. You could actually say that every time you pedal up a hill, your bicycle is nuclear powered. Yeah, that's kosher. You could say that. You have a nuclear powered bicycle. Sweet. Now that's kind of actually that's a biological way of thinking about energy. Food chain. Food chain from the sun. The baseline of the food chain is the SUN. What we're going to talk about is energy as a dynamical quantity, kind of partnering up with momentum as another dynamical quantity. And just as momentum encodes Newton's law about accelerations and forces, energy is going to be the thing that changes or that encodes changing speeds. And what we're going to try to do this afternoon is figure out how that all works. All right, so as before, we're going to think about trajectories, a path. and a path for which an object, along which an object is moving, an object that experiences a force. Okay? Because the idea of energy and path and force are all related together. And here's the key question. We're concentrating on changes in speed, speedometer. And we're not paying attention to direction so much as we are to speed. Now, if you're on a path and there's a force that's tangent to the path, i.e. parallel to the velocity, because velocity is always tangent to the path. So if your force is parallel to the velocity, tangent to the path, or maybe anti-parallel to the velocity, which means exact opposite direction. So velocity to the left, force to the right, those would be anti-parallel. If that happens, you will change the speed. If they're parallel, if you have some newtons of force parallel to the velocity, it'll speed up. If you have some newtons of force against the velocity, the opposite direction, anti-parallel, you'll slow down. Okay, net newtons anyways. Now, if you're on a path, you can also have some force that's perpendicular to the path, and we know all about that. We've studied that already. That's centripetal force. If you're on a curved path and you're going at constant speed, you're on cruise control, but you're on a curved path, your force is only centripetal because you're not speeding up or slowing down. So the only force you have is the force it needs to change your direction if you're on cruise control. So a force perpendicular to the path, i.e. right angles to the velocity, that'll change the direction. Now, we're not going to be worried too much about that for the concept of energy. Mostly we're going to be worried about this one up here, A, lowercase a, the force tangent to the path, because that's the one that changes the speed, not the direction. Now, every path in Google Maps, every road can be laid out in segments. If you're on the turnpike heading for Miami, you can see a mile marker. I think it's every 1/10 of a mile or every mile, depending on the road, depending where you are. So you can have a spatial or a temporal segment. Now, we did the temporal segmentation of a freefall path last time, and that was the freefall equal increments of momentum for equal increments of time, the stroboscopic view of a freefall path. Now, what we're going to do today is measure out the same freefall path, but we're going to do it spatially, not temporally. We're not going to use stroboscopic principles. We're going to use other principles, basically a meter stick, to form our image. Okay, and that's using this generic symbol for a spatial increment, delta S. Okay, so we go from coordinate S1 to S2 to S3 and on down. Or if we're doing a temporal segmentation, T1 to T2 to T3 and on down. All right. Now, this is all going to be feeding into the concept of energy. So let's take a picture. Take a look at a picture. Now, this one we've already done. This is not a good scale drawing. It's carefully done, but it's not perfectly the scale. The basketball's a little bit out of scale. It's a little bit big. But if you time your strobe to flash once per second, you know that if delta t is 1 second, you get equal increments of momentum for each increment of time. So delta p is equal as long as my strobe is firing, uniformly every second in this particular case. Now, this is similar to the one we did the other day, except the other day we used a time increment of 0.25 seconds, quarter of a second. This one will also do 1 second of free fall. All right. Now, I want to introduce some vocabulary here. Delta P is what we would call dynamical, a dynamical quantity. Delta T is a geometric quantity. And you may say to yourself, hey, Dr. B, I never saw anything about time in my geometry book in 10th grade high school class. So what exactly are you talking about? Well, I'm talking about four-dimensional space-time. I'm talking about space and time the way Albert Einstein did. And his conception was that the universe is not a three-dimensional but a four-dimensional universe, and the fourth dimension is time. So if that's really true, which we believe it is, it works. It's a very well verified theory, the theory of relativity, four-dimensional space-time. Then yeah, delta T, that's a geometrical quantity in space-time. So this would be called a temporal partition, partitioned by increments of time. Now what we're going to do is another partition, Caitlin, and this one is going to be spatial. And so go ahead and sketch same free fall path, but now what we're going to do is put little tripwires, and when it passes 18-meter marks, all right, it drops through y equals negative 18 meters, it fires the camera. Okay, so strobe goes every certain amount of time. This one, it only flashes if the basketball hits a certain, so it's like a tripwire. Or if you were in like a spy movie, Austin Powers spy movie, lasers to set off the camera. And the lasers at 18 meters negative, negative 36 meters negative, negative 54 meters negative, yeah. That's good. That's a spatial partition. The geometric quantity is delta y. So now I'm not using the generic term delta S. I've got a coordinate system chosen. It's the y coordinate, so the up and down. Delta y. And so I'm saying I'm recording the position and the dynamical quantities every 18 meters of drop distance. All right, so that's the spatial partition. Same free fall trajectory, just a different way to look at it. And so the question could come up, all right, on my temporal partition, Darion, if I go equal delta t's on that temporal partition, I get equal delta p's. So if I go equal delta y's over here, do I get equal delta something else? In other words, is there a dynamical quantity that has equal increments when you style the path this way as a spatial partition? And here's another way of asking that same question. Here's my geometrical quantity. Is there some quantity u that on this partition you get equal bite-sized pieces of delta u? If so, what is it? What would that dynamic, because we got one over here for temporal, it's delta p, temporal partition, delta p, equal pieces, equal bite-sized pieces. So it's logical to ask spatial partition, what kind of equal bite-sized pieces do you get over here? Or do you? Do you get one? Is there one? And the answer is yes. And that quantity is called energy. So energy can be thought of as a dynamical quantity associated in a four-dimensional space-time with equal increments of distance on a free fall trajectory. It's a lovely way to think about it. And if Galileo had known a little bit of relativity, which he was definitely smart enough to have done, he might have discovered all that stuff 400 years ago. But we're doing all right. We're doing all right. So we think fourth dimensionally, and what we're going to do now is use the analogy in a slightly different way. We're going to look at a formula that we have used already, the impulse formula. And that one is oriented to delta P. All right? And it has a geometric quantity in it, delta T, and a force. So it's logical if we have some new quantity, delta U, is it going to be a net force and a delta S? Because delta P is a net force and a delta T. All right? So four-dimensionally flip-flopping, four-dimensionally analog, should it look something like this? Now remember, the delta S is my generic notation for any spatial increment, whether it's left, right, delta X's, left, right, up and down, delta Y's, forward and back, delta Z. Could be any of those. Could actually be delta R if you're thinking about a rocket launching straight up into space from any position on Earth. Yeah, changing the radial coordinate. Yeah, that would be kosher. Spherical coordinates. Yeah. So let's think about that. And the way that we're going to think about it is using a generic path. So draw a little curvaceous path, G. And pick a point on it and draw in a velocity vector. Just make it a good size velocity. We're not going to make any calculations, but make it big. And mine is slanting up and to the right. All right. And so there's my velocity. And on this path, I might have a perpendicular force. Or I might have something that's parallel, or I might have a mixture of both. And that's what I've got here. So at that dot on the path, draw an arrow now straight to the right, as I've done. And this one is neither parallel nor perpendicular to the path. It is a little bit of both. Okay, so for instance, this would be the force, or this is like the force on a Maserati accelerating through some curves. If you're going through the curves at constant speed, you have some centripetal force perpendicular to the path. But if you're also speeding up, you have some force tangent to the path. And so you have a little bit of force parallel and a little bit perpendicular. So let's take a look at that. All right. So what we're going to do is refine our F up here in the equation. Because we're talking about speed, and F parallel, the component of the force parallel to the path, is the one that changes the speed. Now, let's go ahead and do a copy of force, of the net force. So I just kind of blew it up and shifted it downward. Okay. And what we're going to do is extract the portion of that force that's parallel to the path. So go ahead and your F parallel is going to be parallel to V. So the red velocity vector up here and F parallel, so kind of sketch them in that way. Right? Now, by the same token, F perpendicular, the centripetal part of the force, the perpendicular part of the force, is going to be right down here. So tail to tail to tail. And we've extracted here the part that we care about, F parallel. And the F perpendicular, it's in here too. Now, we don't really need that for the energy. Something else we might need it for, but not for the energy. F parallel is all that we need for the energy considerations. And those two components F perpendicular and F parallel, they form a right triangle. There's the right triangle. They form a right triangle, and the hypotenuse of that right triangle is the net force itself. Okay, so try to sketch that in, and let me bring this back up here. Take a look at what I've got. There's the right triangle, and here it is. Whoops. Let me go through this again. Blew it. I hit the wrong button. Okay, there's F parallel. Here's F perpendicular. Here they are as a right triangle. And here they are tail to tail. All right, so maybe resketch it. Resketch FNet and then, form this right triangle, and one side of which, here it is parallel to the velocity. And then the third side will be F perpendicular. All right. Now this is my scratch work area down here in the bottom of the page. What I really want to do is sketch this, take F parallel, and move it up here. I did it again. Sorry, you guys. So here comes the right triangle. All right, now move that F parallel up here. Okay, and just kind of sketch it in really nicely up there. All right, and here's where it was, down here. Okay. And this is the portion of FNet that changes the speed. This is the part that we need for our conjecture about delta U. Now, I'm going to give you another clicker question. So hit your refresh key. This is a multiple choice. And just to get your brain thinking about perpendicular and parallel again, answer this question. The parallel component of the net force speeds up the Maserati on the track. What does the perpendicular component, F perpendicular, do for the motion of the Maserati? So go ahead and make a choice. Read carefully, make a choice. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys have got. Uh-oh. Got a little bit of trouble here. Some of you voted for A. The correct answer is C rather. Hey, you guys, make a note in your notes. F perpendicular has another name. It is the centripetal force. And centripetal force on any curved track is the one that changes the direction, even if you're on cruise control. If you're going down a curved track at 25, I don't care how curvaceous it is, the only force you have is a centripetal force. Now let's keep going. So we're going to put that in into the formula, and we're going to rename. It's now not an unknown number. We're going to use the letter W for work. This is the definition of work. F parallel times delta S. And again, that could be any direction of the path. Freefall, that would be delta y. It's pretty easy. All right? And this is the quantity that if you compute this on equal spatial increments, on the spatial partition, you come up with equal quantities of F delta S. Okay, so this is the nice way to express delta U. Right, so let's go back to the partition. So the dynamical quantity corresponding to F parallel times delta Y on this freefall partition, delta Y is the partition. It actually involves V squared, and after you do a little bit of calculus, you come up, and we're not going to do any calculus, but it's not too bodacious. And if you've had calculus class, you might recognize an integral here. This is called the kinetic energy. The kinetic energy formula, 1/2 mv squared. And for some reason, I predict that a lot of you guys will remember this formula 10 years from now. I don't know why. It's just it's stuck with me for a long time, ever since I learned it. Kinetic energy. This is the thing that if you calculate it, at equal spatial steps, you get equal changes in the kinetic energy. So equal kinetic energy increments, delta KE, from equal drop increments, delta Y. Now that's on a free fall trajectory. Here's the formula applied to a free fall drop trajectory. Delta KE equals F parallel times delta Y. Hey, you guys, just a word of caution. We're using two capital W symbols now. One for the weight force, W equals mg, and one for work, F parallel times delta x, or in this case, F parallel times delta y. So the work, or the increments of work, use capital W. So be aware of that as you read. Be alert to the context, and as I always say, read carefully, and you'll be able to tell which symbol is which is being talked about. So now we've completed our analogy. We've got a dynamical quantity that comes in equal bite-sized chunks if you have a temporal partition of a free fall trajectory. And here we've got a dynamical quantity, 1/2 mv squared, that comes in equal bite-sized chunks if you divide up the same partition along a spatial basis. All right, so here's a summary. And so now we've got, if Albert Einstein was sitting in the back row, hey, wait a minute. No, that's not. That's some guy wearing a Batman t-shirt. If Albert Einstein were sitting back there, he'd be going, yep. And, by the way, this puts you have now matriculated. You're still in the school of Galileo, but now you're in the College of Einstein, Einstein College. We are now thinking four-dimensionally. So your dynamical quantities are momentum and energy in general. They come in equal bite-sized pieces, depending on how you partition your free fall trajectory. Now, final comment for you is simply this. In the metric system, 1/2 mv squared, so kilograms times the square of a speed, that's kilogram meter squared per second squared. That's known as a joule, Joule. And that is named after a British scientist named Joule. And hey, you guys, it's also handy sometimes to express an energy in Newton meters, because 1/2 mv squared mass times the square of a speed has the same units as the force times the distance, F parallel times delta y. So we'll work out some examples next week and in homework where Newton meter is a handy expression to use for canceling. All right, let's dismiss. You'll have homework 11 available by lunchtime tomorrow, due on Wednesday. I'll see you next week.